Tonight, cell phones. Whatever you think you've heard before, you must pay attention to this report. The industry insists they're perfectly safe.
There is not a linkage between the use of wireless phones and health effects.
But now, there are new warnings just made public about children and cell phones. Serious new questions. And this man, head of the industry's research program for 6 years, no longer keeping silent about what he knows.
We now have some direct evidence of possible harm from cellular phones.
When 2020 put some of the most popular cell phones to the test, we came up with surprising results. Chief Investigative Correspondent Brian Ross with a report everyone will be talking about. Worry about your wireless.
All right, so I recorded this video clip roughly about 20 years ago, believe it or not. We're still discussing the same issue. Cell phones, are they safe? All right, so we'll just put that debate to rest today, hopefully.
Tonight, cell phones. Whatever you think you've heard before, you must pay attention to this report. The industry insists they're perfectly safe.
There is not a...
Anyway, so I don't know, roughly about 10 years ago, I'm in Turkey and I talked to one of my relatives. This guy's a business person. And then just when we were about to leave, he goes, "Can I have your number? Cell phone number?" I said, "No, you can't." And then he was a little bit startled. He seemed a little bit offended as well. He said, "Oh," I said, "Because I don't have a cell phone." And then his first question is it because of radiation? And then I was startled. I said, "No, not because of radiation. I don't want to make myself available to anyone to that extent. That's the reason why. I don't even walk for it, guys. Seriously. Cats meow, dogs bark, people talk, it's white noise. All right, so I'm very particular about my time. So that's the reason why I didn't want to have a cell phone. And then as soon as he said that, I'm thinking, what do you mean by radiation? So he hands me over his cell phone. I'm looking at it, and it says, warning on it, this may cause cancer. The sort of stuff that you would see on cigarette packages. And I said, how would you know that? So they've been doing research on it forever. And my next question is, why is it that we don't know about it in the United States? Cell phones, guys, what kind of radiation do they use? All right, as soon as I ask this question, what do you guys are thinking? I know exactly what you guys are thinking because I've been doing this stuff for a while. You guys are thinking that the cell phones use radio waves, right? Not really. All right, they don't use radio waves. The radio wave frequencies are taken up for commercial as well as military usage. That stuff is not available. So if it's not the radio waves, what kind of radiation do you think they're going to be using? All right, and next question is, would that be harmful? All right, so that's the sort of stuff that we'll get into.
Let's go to science class for Bill and Ted's excellent microwave experiment. Microwave manufacturers are very strict about the types of things you should put in their ovens. No aluminum foil, no metal pots or pans, and certainly no eggs. Apparently, Bill and Ted didn't read the excellent directions.
Why did the egg explode? You guys kind of know the answer, right? All right, so what happens? It's heated up. With heat, the pressure went up. Inside was pressurized. You crack the shell, end up getting an explosion on it. Simple. Do you guys know that you can do the same thing using a piece of grape? Just heat it up. And then it doesn't happen all the time, but when it does, it's phenomenal. The only thing you have to do is just cut the skin with something. And then you end up getting an explosion. It's going to stick to your skin. You're looking at first and second degree burns. It's not going to be a fun experience, but obviously you're going to get an explosion on it. You can also do the same using a glass of water. That's all you have to do. Just heat it up. Just boil the water. And then watch the bubbles form. And then let it cool down and go back, boil the water again 10 minutes later. And then watch the bubbles form. And then 10 minutes later, just go back and boil the water and keep boiling until no more bubbles. At that point, you can take it out and then just shake the water if you want to. And then you're going to end up getting this amazing explosion. It can explode all the way up to the ceiling. Once again, if it hits your skin, we're looking at first and second degree burns. So that sort of stuff is dangerous. It's called superheating. So what's causing that to happen? Microwaves, how do they cook? That's what the question is. Out of all the questions that I have, the least interesting to you is the nature of light. What's light? Is it composed of waves or is it composed of particles? All right, so that's the stuff that we're going to focus on. If you're a physicist, this is the most exciting and interesting question. And if you're a non-physicist, you're thinking, oh, everything else was amazing. And what's going on with this one? Are we going to talk about the nature of light? Who cares? Well, you will, shortly. So we talked about waves, and today we're going to be talking about the electromagnetic waves. So you know what a wave is? Wave is a disturbance that carries energy, right, from one place to the next place. So a traveling disturbance is called a wave. And then one thing that we know is that it's going to be carrying energy. We've seen this before, so falling dominoes is an example of a wave. Because we got this disturbance, it's traveling, and we also know that it's carrying energy because it's able to apply a force on something and be able to make it move well in the direction of the motion, right? So that's a wave. Periodic wave is a repeating wave. wave that goes in cycles is known as a periodic wave. Went through the definitions. We know what an amplitude is. That's the maximum height of a wave. So that's the maximum displacement with respect to the undisturbed position, which is in the middle. We know what a wavelength is. That's the length of a single cycle. So that's your wavelength. You get to use the letter lambda for that. We know something about the period. The period is the amount of time it takes for a single wavelength to form or single wave to form. All right, it's the amount of time it takes for a single cycle to form. Frequency is the number of cycles per second. There's one single cycle, there's the second one, the third one, and so forth. It's going to be the reciprocal way. It can be expressed in terms of hertz. All right, so electromagnetic waves is the title of today's lecture. These are actually three-dimensional waves. All right, so you got one component of the wave going up and down, so that's the electric field component. And then 90 degrees to it, you will have the magnetic field component. So the green is the magnetic field component. All right, so this becomes an electromagnetic wave. It's traveling from left to right at the light speed. All right, so the electromagnetic waves will have an electric field component. So it's going to be undulating up and down. And then wrapped around it, you will have the magnetic field component. So all electromagnetic waves will travel at the light speed. Speed of light in a vacuum. All right, the C is known as the light speed. In a vacuum, it's going to be 300 millimeters per second, 189,000 miles within a single second, or 670 million miles per hour. Okay, so what does that mean? Which means that within a single second, the light travels roughly about 190,000 miles. And within an hour, it's going to travel 670 million miles. That's what it means. All right, so speed of light, nothing moves faster than light speed. All right, so that's going to be constant. So all electromagnetic waves will travel at the light speed. So you got the electric field component, and you got the magnetic field component, and everything is traveling at the light speed. Despite the fact that all electromagnetic waves travel at the light speed, all right, so the speed of light is going to be constant. Wave speed can be expressed in terms of a combination of the wavelength as well as frequency, and which means that the waves can have different frequencies and different wavelengths. All right, so for a given constant speed, in this case, the speed of the light speed is going to be constant. If you increase the frequency somehow, the wavelength is going to become shorter. If you reduce the frequency, the wavelength is going to get longer, which means that the electromagnetic waves will break into an electromagnetic wave spectrum. All right, so within the wave spectrum, what we will do in the upward direction, we'll increase the frequency in this direction, in the upward direction. As the wavelength is shorter, as the wavelength is going to get shorter in that direction. All right, so lowest frequency radio waves. All right, so I'm going to keep increasing the frequency in the upward direction, so we will hit the microwave region. If I keep increasing the frequency in the upward direction, now we will have infrared. And then if I keep increasing the frequency in the upward direction, we'll end up getting the visible spectrum. And then if you move on, ultraviolet, and then we will get X-rays, and top we will have gamma rays. All right, so this is known as the electromagnetic wave spectrum. So frequency increases in this direction. As the frequency increases, what happens? The wavelength is going to get shorter, so it gets smaller. All right, so the lowest frequency radio waves, the highest frequency gamma rays. That's what it means. All right, so let's reverse the order. All right, so lowest frequency radio waves is going to be the largest wavelengths. All right, so the wavelengths will be the largest. At the gamma ray region, the wavelengths will be the shortest. So the frequency goes up, the wavelength becomes shorter. Frequency goes down, the wavelength gets larger. That's what it means. All right, so all electromagnetic waves will travel at the same speed, but they're not going to have, they don't need to have the same wavelength and frequency. All right, so as the frequency changes, the wavelength is going to change in the opposite direction. All right, so radio waves will have the lowest frequency, the gamma rays will have the highest frequency. If that's the case, here's a question for you. Which portion of the electromagnetic wave spectrum moves fastest, the gamma rays or the radio waves? The answer to that question is all will travel at the same speed in a vacuum. And so it doesn't matter. Which portion has the largest wavelength? Radio waves. Which portion has the largest frequency? Gamma rays. Which portion has the smallest wavelength? Gamma rays. Which portion has the smallest frequency? Radio waves. All right, so we got the best answer. All right, so which one is not true for electromagnetic waves? We know the answer for that one, right? What's not true is they travel at different speeds in a vacuum. They all travel at the same speed. So that statement is not true. That statement is not correct. All right, sometimes it does this, and it's going to be somewhat annoying. All right, just want to make sure.
Professor James Clerk Maxwell believed in Faraday's far-sighted vision, and he had the mathematical skill to prove it. Maxwell and the aging Faraday became close friends.
James, forgive me. A word of advice. Don't get over it.
Michael, how are you?
I'm fine. Memory isn't too good.
Well, I thought you might like to see what I've just published.
Oh, yes, yes. Splendid.
So your results show that when electricity flows along a wire, what it actually does is create a little bit of magnetism. And as that magnetic charge moves, it creates a little piece of electricity. Electricity and magnetism are interwoven, like a never-ending braid. So it is always pulsing forward. It's wonderful. Michael, there's something very crucial in maths. This electricity producing magnetism and magnetism producing electricity, it can only ever happen at a very particular speed. The equations are very clear about it. They come up with just one number.
Light moves incredibly fast, 670 million miles per hour. That's why scientists use the term C. It stands for celeritas, Latin for swiftness. Long before the 19th century, scientists had computed the speed of light, but no one knew what light actually was. Back in England, a man we've already met was willing to make an educated guess. After Sir Humphrey Davy's death, Michael Faraday became Professor Faraday, one of the most important experimenters in the world. The scientific establishment still found it hard to accept that electricity and magnetism were just two aspects of the same phenomenon, which Faraday called electromagnetism. But now, he has an even more outrageous proposal for his audience.
Invisible lines that can emanate from electricity in a wire, from a magnet, or even from the sun. For it is my contention that light itself is just one form of these vibrating lines of electromagnetism.
For 15 years, Faraday...
What's so funny? Is that the British sense of humor that we don't get? Is he joking about something? Why is it that they're laughing? They're laughing because they think that this guy doesn't know what he's talking about. Faraday is known to be an experimentalist. He has no formal education in physics. He's got no background in mathematics. And yet this guy is gifted. He's just coming up with all these ideas. Gives us the Faraday's law. Obviously, he's the guy who came up with the idea of visualizing the electric field, starting at the positive charges, ending on the negative charges. He's the guy who's visualizing and also being able to map the magnetic fields. And so this is the guy who's literally, he's starting a new science. And all of a sudden this guy is thinking, wait a minute, the electricity generates magnetism. And by varying the strength of the magnetic field, you can generate electricity. Is it possible that you can combine them into an electromagnetic waves? This is the guy who's coming up with the theory, and no one is taking him seriously. Because the guy cannot do math. And they're making fun of him. They're laughing because they think it's funny. They're simply making fun.
Faraday struggled to convince the skeptics that light was an electromagnetic wave, but he lacked the advanced mathematics to back up his idea. Eventually, someone came to his rescue.
The guy who came to his rescue is this guy. His name is Maxwell. James Clerk Maxwell. Einstein's idol. This guy is a Scottish theoretical physicist. He's the best of his day. And he idolizes Faraday. Imagine that. He's much younger than Faraday. He idolizes Faraday. And he takes it upon himself to prove Faraday is right. All right. He starts formulating all these ideas that Faraday came up with. And he was able to express all these ideas in 4 equations. All right, so I'm not going to take you through each and every single equation because this is college physics, obviously. But I'm going to take you through the ideas behind it. All right, so what Maxwell does, it comes up with 4 equations. These are known as the Maxwell's equations. And then combining those equations, he figures out the speed of the electromagnetic waves. This is what happens. The speed of electromagnetic waves is this number. You guys have seen this number, but that's the speed of light. All right, we talked about epsilon naught, mu naught, and all that stuff. I said, you know, this is known as the space permittivity constant. This is the space permeability constant. Somehow they would put the brakes on in terms of how fast the electric and magnetic fields could travel in space, in free space, in essence. As it so happens, when Maxwell came up with his own mathematics and figured out the speed of these electromagnetic waves, he came up with this number. He came up with the speed of light. So what does it mean? Which means that the electromagnetic waves travel at the light speed. What else travels at the light speed? Light does. So what does it mean? That means that light is also an electromagnetic wave. So he published his findings in 1865, roughly about 150 years ago. And then now the talk.
Professor James Clerk Maxwell believed in Faraday's far-sighted vision, and he had the mathematical skill to prove it. Maxwell and the aging Faraday became close friends.
James, forgive me. A word of advice. Don't get old.
Michael, how are you?
I'm fine. Memory isn't too good.
Well, I thought you might like to see what I've just published.
Oh, yes. Yes. Splendid.
I love this scene. All right, so this is PBS, and this is PBS at its best. It's nova. Einstein's great idea. Based upon the book E equals MC squared by David Bodanis, the historian. I love this scene because Maxwell just published his paper, and he is sharing his findings with Faraday. Maxwell is a theoretical physicist. If you've never seen an article, if you've never seen a paper published by a theoretical physicist, guys, let me tell you what it looks like. It's equations all over the place. All right. If you're a physicist, if you're a specialist in that field, you can read those papers, you can visualize the math. If you're not a physicist, if you don't have any sort of background in mathematics, you might as well be reading something written in Chinese if you're not Chinese. You're not going to be able to understand what you're looking at. And that's what the situation is at this point. Faraday is looking at the paper, written in mathematics by Maxwell. He doesn't know what he's looking at. And the math that he's looking at is the expression, mathematical expression of everything that he's been talking about. Everything that he was visualizing.
So your results show that when electricity flows along a wire, what it actually does is create a little bit of magnetism. And as that magnetic charge moves, it creates a little piece of electricity. Electricity and magnetism are interwoven, like a never-ending braid. So it is always pulsing forward. It's wonderful. Michael, there's something very crucial in maths. This electricity producing magnetism and magnetism producing electricity can only ever happen at a very particular speed. The equations are very clear about it. They come up with just one number. 670 million miles per hour.
What is that? Is this speed of light expressed in terms of miles per hour?
I'm not sure.
It's the speed of light. That is the speed of light. You were right all along. Light is an electromagnetic wave.
Maxwell had proven Faraday right. Electricity and magnetism are just 2 aspects of a deeper unity. A force now called electromagnetism, which travels at 670 million miles per hour. In its visible form, it is nothing other than light itself.
Electromagnetic waves, how are they generated? In Faraday's mind. All right, so here's the way Faraday was thinking about it. All right, so get a wire, attach it to an AC generator, alternating current generator. Right? So what's going to happen is the current is going to go up and down just like that. Current is going to go up and down, number of times per second inside this wire. Right? What's driving the current up and down? The electric field is. So what happens to the electric field driving the current up and down? It's going to get radiated in the wire. All right. So the electric field is going to push the charges up and down, and then what happens is it's going to get radiated in the wire, and that's what's happening. So electric field pushing the charges up and down, creating an alternating current inside the wire, gets radiated away. So this is how you get the electric field component of the electromagnetic wave. Where do you get the magnetic field component? All right, so what happens when there's current? It generates magnetism, right? Notice that the magnetic field wraps itself around the current. By the way, what drives the current? The electric field does. Also, in essence, what's happening is the magnetic field wraps itself around the electric field. All right, so the electric field is moving in the upward direction, the magnetic field is going this way, electric field reverses direction, now the magnetic field is going the other way. And you know what happens to the electric field? It's just radiating away. So what do you think is going to happen to the magnetic field? It's just going to wrap around the electric field. As a result, we end up getting the electromagnetic waves. All right, so this is exactly the way Faraday was visualizing. All right, he thought that the field would be radiated away from the source. It would have an electric field component and would have a magnetic field component. And the magnetic field component would wrap itself around the electric field component. So any variation within the strength of the electric field component creates the magnetic field component. Any variation within the magnetic field component creates the electric field component. All right, so that's how electromagnetic waves are generated. All right, so the electric field is going to be produced by the magnetic field component, right? It's going to be a change in magnetic field. C is the best answer. All right, so the changing electric field is going to produce the magnetic field component. All the electromagnetic waves will travel at the light speed. Oh my God, this is so awesome. So the nature of light is a wave. Except we got a few problems. If nature of light is a wave, what's the definition of a wave? The definition of a wave is a disturbance that travels, in this case, traveling at the light speed. That carries energy with it, right? That's what a wave is. What determines how fast the wave travels is the medium itself. So if that's the case, the question is, what is the medium that the light is disturbing? So the light travels at the light speed in a vacuum. So what is the medium that the light is disturbing so that it can travel at the light speed? All of a sudden, that became the question. Seriously, guys, the vacuum. What is the medium? All right, so what determines how fast the wave travels is going to be the properties of a material, properties of a medium. Except if you're dealing with the vacuum of space, which is empty because it's a vacuum, it's got nothing that produces tension and it's got no molecular density. So if that's the case, what is the medium that the light is disturbing so that it can travel at the light speed? All right, so in the absence of what's visible, they decided that there must be a special medium that the light, only the light can disturb. All right, that's what Maxwell believed in. That medium is called or dubbed ether. The idea was first proposed by this guy, Huygens. Okay, more about Huygens later on. Okay, I think it's coming next week. And all of a sudden, they know that the light is a wave, it's an electromagnetic wave, and then we know that space is supposed to be a vacuum. It's got no molecular tension, it's got no molecular density. There's no tension of empty space, and there's no absolute no density of any sort if you're dealing with a vacuum of space. So the question becomes, what's being disturbed? And then they came up with this theoretical medium, and they call that the ether. And there's a second question that we need to focus on. Light travels at the light speed relative to what? If you're a theoretical physicist, it travels at the light speed relative to this point that you're looking at, P. All right, so relative to that point, the light is going to travel at the light speed. Right? If I'm driving my car at 60 miles per hour, I'm driving my car at 60 miles per hour relative to the surface of the Earth. Relative to Earth, I'm driving my car at 60 miles per hour. All right, it seems fairly straightforward, but I got news for you guys. The Earth is spinning on its axis as well. It's not stationary. It feels stationary, but it's not. It's spinning on its axis roughly about 1,000 miles per hour. And then on top of that, we're also moving in space relative to the sun. I don't know, like 60, 70, 80,000 miles per hour. I don't recall the number exactly, but we are in motion. The sun is not stationary either. The sun is also moving relative to the center of our galaxy, close to the speed of light. Everything is in motion. So when somebody says light is moving at the light speed, the question becomes relative to what? All right, relative to what? Relative to this point? So the question is, what if this point is also moving at the light speed? Then what happens to light? So that becomes the
It is
question that Einstein comes up with.
nothing other than light itself.
So Einstein is 16 and reading Maxwell's paper, which was published in 1865. Maxwell is Einstein's hero. He's reading the paper, he's thinking about it. I mean, in theoretical physics, when you solve a problem like that, you know, relative to this point, it's going to move at the light speed. So Einstein says, yeah, wait a minute. What if this point is also moving at the light speed? Then what? Then what happens to the light? All of a sudden, this becomes the question of, what if I'm traveling at the light speed with a mirror in my hand? Would I be able to see my reflection? Now, for you to be able to see your reflection, the light still has to move at the light speed relative to you, right? If light is still moving at the light speed relative to you while you're traveling at the light speed, shouldn't that light traveling at double the light speed relative to me when I'm just sitting here just watching Einstein travel at the light speed? And then it gets really bizarre.
It is nothing other than light itself. And nothing fascinated the young Einstein more than light.
We have lectures in half an hour.
Oh, let me think. Professor Weber and his life-draining monologue, or you, Mozart, and James Clerk Maxwell.
We can't. We'll get a warning.
Our project is too precious to waste time listening to those dullards. Come with me. We'll read Maxwell and think about the electromagnetic theory of light.
Oh, why, my dear little Johnny. How you enchant a lady. She's very pretty.
Yes. But can she soar and dance like our dark souls do?
Maxwell's equations contained an incredible prediction. They said you could never catch up to a beam of light. Even if you were traveling at 670 million miles an hour, you would still see light squiggle away from you at 670 million miles an hour.
You see how she stares that way?
Yes?
You see how for her it is static?
Yes?
She and the wave are traveling at the same speed. We see the wave moving through the water, but relative to her, it just sits there. So is light like that?
Common sense would say that if you caught up to a light beam, there would be a wave of light just sitting there. Maybe it would be shimmering, a bit of electricity and a bit of magnetism.
So if she was traveling alongside the light wave, it wouldn't be moving, it would be static. But Maxwell says you can't have static light.
Maybe Maxwell is wrong. Maybe if you catch up to light, it is static, Albert, like a wave next to a...
Imagine if I was sitting still and holding a mirror to my face. And the light travels from my face to the mirror, and I see my face.
Yes?
However, if I and the mirror were traveling at the speed of light...
You're going at the same speed as the light leaving your face.
Exactly.
The light never reaches the mirror.
So would I be invisible?
That doesn't make sense.
Young Einstein was starting to realize that light was unlike any other kind of wave. Einstein was about to enter a surreal universe where energy, mass, and the speed of light intermingled in a way no one had ever suspected.
It took Einstein 10 years to solve that problem. And so these are the questions. These are the questions that we will get to investigate. All right, so all electromagnetic waves travel at the light speeds. So the question becomes relative to what? All right, so relative to what? Light travels at the light speed. All right, so if light is an electromagnetic wave, what sets the speed of a wave is the medium itself. So the characteristics of a medium is going to set the speed. The only thing we know is the vacuum of space contains nothing. You will probably find a hydrogen atom here and there every 100 miles or so, but that's the extent of it. Right? It's almost got zero density, and there's absolutely no molecular tension. So there has to be a medium for the light to disturb if it's a wave. Maxwell knew that, so they came up with the idea of an ether. Ether is the medium that light was supposed to disturb. It's a theoretical medium relative to which the light travels at the light speed, obviously. So the light is going to travel at the light speed relative to ether. And Einstein is reading Maxwell's equations, the paper on the reading Maxwell's paper on electromagnetic waves, and all of a sudden he focuses on the question of relative to what the light is traveling at the light speed. All right, so when something is traveling, it's traveling at a given speed relative to something. All right, so if that's the case, with respect to what the light is traveling at the light speed? becomes a question. And in Maxwell's mind, it's traveling at a light speed relative to this theoretical substance, which they call ether at the time. And in Einstein's mind, and this Einstein is still a kid, he's 16 years old, he's reading this paper, written in a theoretical physics journal. And he says, what if there's no ether? He's not convinced that there is ether. He says, what if there's no ether? And if there's no ether, what if this point is also traveling at the light speed? Then what happens to light? Does light still travel at the light speed relative to this point, even if this point is traveling at the light speed? All right, so it's translated to English, that becomes the question of what if I'm traveling at the light speed with a mirror in my hand? If I were to look into the mirror, would I be able to see you? All right, so these are all the questions that I'm seeing right now that we will actually explore in the future. All right, so let's talk about electromagnetic waves. Let's check to see how each and every single portion of the electromagnetic field is generated. Right, so the lowest frequency, the highest wavelength, is the radio wave. We generate the radio waves using AC circuits, oscillator circuits. It's an AC circuit, which means that we oscillate the current. That's what we do, which means that the current goes up and down. So we keep changing the direction of the current. So I just get a piece of wire, we call it an antenna or a transmitter. And within that antenna, just keep changing the direction of the current between 10,000 to 100 million times per second. So that range is known as the radio wave range. So it's 10,000 to 100 million times. All right, so we end up using AC circuits, which means that we use alternating current circuits to keep changing the direction of the current within the wire, so AC is the best available. All right, so that's how we generate and transmit the radio waves. All right, so there are two types of antennas that you can use in order to receive the information. Everybody uses cable today. They used to have these loop antennas for TVs 20, 30 years ago. All right, so if you have this kind of an antenna, the whole idea is, the purpose of the antenna is to intercept the magnetic field component, right? So what's happening is the magnetic field is being intercepted by the antenna. Notice that the strength as well as the direction of the magnetic field keep changing inside the area of this loop. So as a result, it causes an alternating current within the antenna, within the wire of the antenna. And then you have the circuitry that's going to encode the message for it. Right, so that's how these antennas were designed to work. Our regular antennas, I'm talking about the radio antennas, notice that they're vertical. Okay, they're designed to intercept the electric field component. What's happening is the electric field goes up and down, and obviously you got charges, conduction electrons inside the metal conductor. So the charges go up and down, so it generates a current. And once again, you got the electronics that's going to decode the information for you, so you can actually listen to the radio station that you want to listen to, or watch the TV station that you wanted to watch. Today, obviously. All right, so the electromagnetic wave is radiated by a straight wire antenna. That's oriented vertically, right? So what should be the orientation of the straight wire receiving antenna? All right, so notice that the electric field component is radiated vertically, so that's the vertical direction. Antenna needs to be in the same direction. So antenna also needs to be vertical. So he's the best answer. Microwaves is even a higher frequency region than the radio wave region. Remember, radio waves will go up to 100 million cycles per second. Once you get over 100 million cycles per second, now we are within the microwave region. Microwave region that we were looking at is 100 million to this is a trillion cycles per second. This is the region. All right, so the electromagnetic wave is going up and down between 100 million to a trillion times per second, cycles per second. That's your microwave region. Now you cannot use wires for this purpose, because what's going to happen if you move the charges up and down inside the wires between 100 million to a trillion times per second, the wires will heat up. All right, so there's going to be a lot of resistance. It's going to heat up. You can melt. So instead, we use vacuum tubes. And inside vacuum tubes, we have electrons. So these are known as electron tubes. So what we do basically is we take the electrons and we jiggle them up and down between these two numbers in order to generate microwaves.
Let's take a moment to find out how microwaves actually work. A microwave oven uses radio waves to cook food. A device called a magnetron bombards the inside of the oven with radio waves, which react with water molecules in the food, causing them to vibrate at enormous speed. That friction creates heat, which cooks the food.
The Amana radar range microwave oven is quality.
In the early days, it was hailed as a revolutionary kitchen convenience.
The family-sized turkey. 675 watts of cooking power means faster cooking than most other microwave ovens. Uses 50 to 75% less energy than a conventional electric range. 5 and 30-minute timers with automatic defrost cycle.
This store has been selling microwaves ever since those heady times.
Is this the soul of the microwave oven?
Or the heart of the microwave. This is a little radio transmitter, and you plug it in, and it converts it to DC voltage, and out comes the microwave.
Let's have fun with commercial TV. All right, guys, when you guys are watching TV, your experience is completely different from my experience. When I'm watching it,
radio waves to cook food. Moment to find out how microwaves actually work. A microwave oven uses radio waves to cook food.
Radio waves to cook food? Let's think about it. I wonder what radio station it's tuned to so we can also listen to it. Why don't you just stick your head in it and find out? Just dial it up first. If it were to use radio waves, it would have been called a radio wave oven. Obviously, they're not using radio waves, they're using microwaves.
A device called a magnetron bombards the inside of the oven with radio waves.
Microwaves.
Which react with water molecules in the food, causing them to vibrate at enormous speed.
I don't think so.
That friction creates heat.
Friction doesn't mean anything at that level. So that's complete nonsense.
Which cooks the food.
Not really, not really, not really.
The Amana radar range microwave oven is quality.
A lot of the science is made up. So what's going on inside the microwave oven that allows you to be able to cook? All right, guys, the region of the electromagnetic wave spectrum, which is responsible for cooking, obviously, the microwave region that we're focusing on. Within the microwave region, what's happening is the electric field goes up and down, right? While it's traveling at the light speed, while it's going up and down between two numbers. And this region is between 100 million seconds per second to 1 trillion seconds per second. All right, cooking usually happens close to 1 trillion seconds per second. I don't remember exact number where it's happening, but for us to be able to cook something, what needs to happen is it needs to kind of match the resonant frequency of water or polar molecules making up the structure. Okay, I said the resonant frequencies. Okay, we talked about resonance last time. So the resonance is what happens when you match one of the natural frequencies of anything externally. What happens is that amplitude of that frequency is going to become amplified. That's what it means. So this thing is just going up and down, say about 1 trillion times per second. And I'm just going to guess that the water molecule has a natural frequency at 1 trillion times per second. It's not trillion. I know that. I just don't recall the number right now. I have to look it up usually at Wikipedia. So when you're dealing with water molecule or polar molecules, which means that one end of it is going to be slight positive charge, the other end is going to be slight negative charge. So the electric field is going to be acting on the positive charge. It's going to push the positive charge in the upward direction and repel the negative charge in the opposite direction, right? So what happens when the electromagnetic wave goes through this water molecule, all right? At this point, it's pointing in the upward direction, and then it's going to point in the downward direction, and then it's going to point in the upward direction. It's going to do this like 1 trillion times per second. As a result, what happens to the water molecule is going to start to spin. So it's going to cause these polar molecules to spin. Right? It could be sugar molecule. It's usually mostly water. And the polar molecule is going to start to spin. So when these molecules are spinning, what happens around these molecules? Imagine that you got a meat molecule right here. All right, so I'm not a chemist, so I'm going to make up chemistry at this point. So the meat molecule looks like meat. And then we will have an ice cream molecule nearby. So what's going to happen is these other molecules are neutral molecules. They're not polar. But what happens is they become polarized. When this negative charge this end becomes positive charge, when this positive charge this end becomes negative charge. So there's always going to be attraction and repulsion among the molecules. So these things are going to start to vibrate. So the vibrational motion of these molecules, when they're vibrating over 1 trillion times per second, this is 1 trillion times per second. That radiation is known as heat, so it causes heating. All right, so when the frequency is more than 1 trillion seconds per second, the heat is generated. So the spinning polar molecules, like water molecules, will set the surrounding molecules in random rotational and vibrational motions. And that random rotational and vibrational motion is known as heat. As a result, what happens, this thing is going to start cooking. All right, so microwaves will not vibrate anything. It's just going to take these polar molecules and then spin these. It's going to spin these polar molecules, and the spinning polar molecules will set the surrounding molecules into random rotational and vibrational motion. It experiences heat, and that's the extent. All right, so the best answer in this case is going to be A. All right, so the next question is, the microwave ovens, do they cook from inside out or outside in? All right, so just make up your minds. If you're right, you will get to give yourself 5 points. All right, so the microwave ovens, will they cook from inside out or outside in?
Besides,
here's what I like about Mythbusters.
for the myth to work, microwaves would have to cook from the inside out, and that's easily tested. Simply throw a roast in a microwave for 20 minutes and carve.
That, I mean, it's totally cold on the inside. It's not heating from the inside out. It's definitely heating from the outside in.
Yeah. The myth is totally busted.
Besides, for the myth to work,
that was conclusive. That was beautiful. All right, guys, the things will cook from outside in. Why? It's kind of weird. But half of you guys didn't expect that. Why would that be happening? Why is that it's cooking from outside in? Why not from inside out? The reason is because of the wavelength. Microwaves, they have relatively large wavelengths. In terms of millimeters, this and that, but it's still relatively large. The larger the wavelength is, the less it's going to penetrate through materials. That's what it is. All right, so the radio waves don't really penetrate through skin that much. The microwaves will not penetrate through skin that much either, normally, or the food in this case. But depending upon the proximity of the material to the source, there's going to be a bit of penetration. So which means that the microwaves will be able to penetrate into the meat, in this case, probably about an inch, inch and a half, possibly 2 inches, and it's not going to be able to penetrate any more than that. So what's happening within this region is it starts to cause spin motion of the molecules, the polar molecules. The spin motion is going to cause vibrational motion. And the vibrational motion gradually will start to travel inward in the form of heat. So the heating is going to start from outside. It's going to move inward. All right, so that's one of the things that we need to remember. Microwaves, for the most part, they're harmless. All right, they're harmless because they're relatively large. They have relatively large wavelengths. Bigger the wavelength is, the less harmful it is. It's not going to be able to penetrate too much into your body. All right, so it's not considered a harmful radiation, provided that the source of the radiation is away from your body. Inside a microwave oven, it just you generate this standing wave pattern, and at certain locations, it's just going to heat up, in essence. And so that's what's happening. So it's going to cook from outside in. Infrared, translated to English, that means heat. All right, so how do we generate heat? We discussed that a number of times. The heat is generated by the random rotational and vibrational motion of the molecules and the materials. All right, so the region is going to be, its frequency range is between 1 trillion to 100 trillion seconds per second. That's when you generate heat. So that's known as the infrared region is what we experience as heat.
Hyenas have excellent night vision. Surprisingly, so do goldfish. These fish see 4 primary colors compared to our 3. They also see an ultraviolet and infrared, the far end of the red spectrum of light. When we change the channels on the TV remotely, we're using an infrared beam. Channel surfing is fish hell. Infrared vision helps fish see in the dark as well as through murky water. We will never know how the world really appears to a goldfish.
And you know what? We don't care. The only thing that we care, though, is the following.
You use your microwave every day, probably without thinking about it. But tonight we're going to show you again how it can cause a dangerous explosion in your kitchen. It involves a bizarre phenomenon. Before you use your microwave another time, you really must see what Chris Cuomo found in this Primetime Owner's Manual.
At about this time last year, Patty and Dave Long of Naperville, Illinois, were preparing for Easter.
It was Good Friday. The kids were off school.
Time to make Jell-O Easter eggs. Patty put the water in the microwave for 3 minutes to boil, but something seemed wrong. No bubbles.
So I hit the ad 30 seconds, and I stood and watched it. But it wasn't boiling. I thought, well, you know, it's got to be boiling. Something has to be wrong.
Patty had been using a microwave for years. She was confused.
So I opened it up, I brought the container out, and I just kind of brought it down like this. So I was going to touch it with my right hand. And before I got my right hand there, I heard this like a whoosh, and I got hit with all that water into my face.
It exploded.
It exploded like a bullet. It just hit the ceiling, too. There was no water left in the cup.
Patty had 1st and 2nd degree burns all over her face. Even worse, the corneas of her eyes had been scalded.
The whole eye was burned, and they were swollen on the inside, so it was blocking some of the vision because of the swelling inside the eye from the heat.
Were you afraid that you may have gone blind?
Yeah, I was afraid I'd never see my kids again.
It would take 6 months of treatment for Patty to fully recover her sight. Still, no one could explain what had caused this accident.
It really wasn't until I got home and saw the water on the ceiling that I really understood that something strange had gone on here, something that I'd certainly never heard of before.
People who have these sorts of accidents are probably reluctant to talk about them because it seems so bizarre and so unlikely. Who would ever expect water, the safest thing we can imagine, to come up and hurt us?
Let us show you what happens in slow motion. Water heated past boiling more than 212 degrees can erupt.
Professor Louis Bloomfield, a University of Virginia physicist, says there's a simple scientific explanation for how these explosions can...
Two or above boiling without any bubbles forming. That's a phenomenon known as superheating. Superheating. Yeah, it's hotter than it should be for normal boiling to occur, and yet it doesn't boil.
Here's why. Something has to start the bubbles forming. Any little imperfection, like the texture of a metal pot, will do. So Bloomfield says, even though it may look unheated, it can actually be superheated.
Now, what does that mean exactly if water's superheated? It's just hot? How's that dangerous? Well, it's almost like a bomb once you've got it superheated adequately, because anything that triggers the boiling, once you've reached that temperature, will cause catastrophic, very sudden flash boiling. Now, can you test this? Can we show it? Well, we've got a container of about half a cup of water here with some red food dye in it, and a little bit of fat floating on the surface, a little oil.
Like it were soup. We microwave the liquid on high power for about 3 minutes. There isn't a flash reaction every time, but this can be dangerous. Don't try it at home. Look what happened to us.
Ready? Let's go.
Bloomfield says all it can take to trigger an explosion of superheated liquid is for something like a fork to break the surface. Then, watch out.
Although an actual liquid explosion is rare, microwave makers put the warnings in their owners' manuals. They say to avoid the danger, stir the liquid before
forming. And
yet it doesn't boil. Known as superheating.
So what's superheating?
Superheating. Yeah, it's hotter than it should be for normal boiling to occur, and yet it doesn't boil.
Okay, so superheating is what happens if you can boil the water above its boiling point. So the water boils at 212 degrees Fahrenheit, right? So which means that if you can get the water temperature above 212 degrees, it's called superheating. So the question is, how do you get it up to that value? The answer to that question is, you can only get it up to that value if there's no bubbles forming. All right, if there are no bubbles forming, then you can get the temperature above 212 degrees. So what happens? It becomes a highly pressurized environment. It's almost like the egg. You just heat it up from inside. And then it becomes highly pressurized. And then what happens when you break the shell? End up getting an explosion. The same thing happens to water. There's surface pressure. The surface pressure is keeping everything together. And then what happens is you go in there, you break the surface pressure by shaking the water up. And then boom, you end up getting an explosion. So the question is, how do you get the heat up the water without forming any bubbles? How does the magic happen? And this guy is an answer for us. He's a Virginia Tech physicist. He will say,
here's why. Something has to start the bubbles forming. Any little imperfection, like the texture of a metal pot, will do. So Bloomfield says, even though it may look unheated, it can actually be superheated.
Now, what does that mean exactly if water's superheated? It's just hot? How's that dangerous? Well, it's almost like a bomb once you've got it superheated adequately, because anything that triggers the boiling, once you've reached that temperature, will cause catastrophic, very sudden flash boiling. Now, can you test this? Can we show it? Well, we've got a container of about half a cup of water.
All right, so what they're getting at is, as long as it's glass of water, because glass lacks imperfections. It's inner surface, right? It lacks imperfections. So nothing is going to trigger boiling. All right, so that's the theory that this guy came up with. So B is the best answer based on what we heard so far. All right, so the question is he right?
It's time now for Adam and Janie to investigate a microwave myth that is potentially lethal.
All right, so this is the sort of stuff that Mythbusters are really, really good at. Okay, it's not the explanations. It's not the physics of it per se, but these guys are amazing at putting together these demos.
If you overheat water in the microwave, you may take the cup out of the bowl, and then the water is going to explode in your face, injuring you or burning you in some horrific way.
We're going to time how long it takes to bubble. After a little research, Adam and Jamie know that the only way water could explode is if it's being superheated, that is, heated beyond boiling point, without actually boiling. Tap water always boils because it has impurities. Distilled water has no impurities. That means no boiling. Put 2 cups of water in the microwave, 1 distilled, 1 tap. When the tap water boils, they'll know that the distilled water has become superheated. Just dropping in a sugar cube should make the boiling process happen instantly and violently.
Spectacular.
That was a flies.
That was exploding water?
It erupted. It left the container.
Yeah.
Quite a bit of it.
If someone were holding the cup, they would definitely have severe burns. But if straight tap water can't explode, how likely is it that people will be scalded by exploding beverages?
On your average day in your average house, it's not very likely. However, with the hundreds of millions of people using microwaves every day to boil water, reboil water, I'd say it could happen a few times a year around the world. Myth, absolutely true.
Okay, here's what I'm going to do. I'm going to take you through the video clip that you guys just saw. It's
time.
Almost 2 minutes.
Time now for
water
could explode is if it's being superheated, that is, heated beyond boiling point, without actually boiling. Tap water always boils.
Tap water always boils.
Because it
you can see it, right? Because has impurities. It's got impurities. whatever that means.
Distilled water has no impurities.
Distilled water, the pure water,
That
lacks impurities.
means no
So, which means that you can boil it without forming in a bubble.
boiling.
So, which means it's not going to boil. You can heat it up without boiling.
They put 2 cups of water in the microwave, 1 distilled, 1 tap. When the tap water boils, they'll know that the distilled water has become superheated. Just dropping in a sugar cube should make a boiling process happen instantly and violently.
It's kind of weird because this is the second time you're watching it. If you're paying attention, this is the first time you're seeing it. This is the first time you're seeing something which I'm about to mention.
Spectacular.
That would suffice.
That was exploding water?
It erupted. It left the container.
Yeah.
Quite a bit of it.
If someone were holding the cup, they would definitely have severe burns.
So what did we learn from that?
Cups of water in the microwave, no impurities. That means no boiling.
Distilled water is not going to boil.
They put tap water always boil.
And the tap water boils. All right, that's it. How about the woman in Naperville? What happened to her? I mean, I know that Naperville is considered to be one of the best places to live in the United States, according to one of the surveys done 3-4 years ago. Is it because the water quality is just so amazingly good that it's like so distilled that it can explode on your face? Is that what it is? Is that the reason why the water ended up exploding? The woman almost got blinded? Or do you think Mythbusters are missing something over here? Because they just said that
it has impurities.
That water is always
that is heated beyond boiling point.
I got news for you guys. You can get it to explode. You can superheat water with anything in it. It makes no difference in reality.
Without. After a little research, Adam and Jamie know that the only way water could explode.
All right, you can put coffee in it, you can put tea in it. The first time around, it's going to form bubbles. Impurities in it is the dissolved gas. So what happens to the dissolved gas? Heat it up, it expands. Now you got your bubbles. And eventually, it's gonna escape from the material. And then you just leave it there. Just let it cool down. And then go back, heat it up again. If it's got gas in it, the gas is going to expand. Once again, you're going to have your bubbles. So let it cool down again. Go back, heat it up. At that point, if there's no dissolved gas inside that water, what's going to happen? You're not going to see any bubbles. At that point, you can superheat it. And then, if you shake it up, you can get it to explode. So that sort of stuff can happen and will happen.
As if it's being superheated.
Unfortunately, though, when you guys are watching this, here's what happens. You're just watching it. And then they already made a statement regarding that tap water is always going to boil.
Water could explode. Is it because
and then here's the visual that you get. If you're not paying attention, and all of a sudden you go, okay, so if it's tap water, you're perfectly safe. Don't bet on it. As long as you're not using distilled water, you think that you're fine.
Tap water boils.
And they go back and they conclude.
Your average house, it's not very likely. However, with the hundreds of millions of people using microwaves every day to boil water, reboil water.
And most people miss this completely. It's really bad editing. This is horrible editing. If you boil water, reboil water, you can't get it to explode. Accidents do happen.
I'd say it could happen a few times a year around, around the world.
A few times a year around the world happens quite often.
This is absolutely true.
At Fermilab, when I was working there, doing research there, they had this extremely powerful microwave oven. And I'm a big coffee drinker, and we didn't have a coffee maker there. So I used to boil the water there, and then like 80% of the time, without even noticing, I would just have it explode. It would be all over the place, and it would just explode despite the fact that there was coffee in it. So I used to spend some time just cleaning up inside the microwave every single week because of that. So it can happen very easily. All right, the visible spectrum is something that we discussed at the beginning of the semester. So the light visible spectrum is the visible that we're dealing with. This happens because of the quantum jump that we were discussing before. All right, so the frequency range is going to be here. So this is going to be 400 trillion to roughly about 800 trillion cycles per second. So this range is known as the visible light range. So our brain interprets this, the visible light, as well as the colors that we see. This happens whenever an electron inside an atom transitions from a higher energy state towards lower energy states. When an electron is jumping around within the atom, what that means is the atom glows, or the electron glows, which means that ultraviolet region is even a higher frequency region than the visible light region. Okay, so discharge element electric arc is responsible for it usually, ultraviolet. When we're dealing with lightning, obviously that's a discharge element electric arc. And that's so it's a higher frequency region. Okay, so now once you reach the ultraviolet region, what's happening is the frequency starts to go up. What happens to the wavelength? It gets shorter and shorter and shorter. Shorter the wavelength is, the more dangerous the radiation becomes. All right, so it's going to start to naturally go through your cells, your skin, your cells. It's going to start to penetrate. Ultraviolet radiation is kind of like beauty, skin deep. Right? It'll penetrate, but it's not going to penetrate too much. It can cause skin cancer. It can cause cataracts, obviously. It gives you vitamin D, so there are some benefits. and it causes aging usually. All right, too much exposure to ultraviolet is going to age the skin. It's going to wrinkle up the skin. If you try to minimize the effects, I mean, by the time you're 90, you're probably going to start looking like 30. You will still die in old age, but your corpus is going to look. All right, and then we got the X-ray. All right, so it's even higher frequency, which means that the wavelength will be even shorter. Shorter the wavelength is, the more it's going to penetrate through the eye. So now you can see through. You can see through the skin.
He's got issues. Nice pants. These things are amazing.
Introducing Dockers Mobile Pen.
All right, so shortly after they had this commercial,
Port of Phoenix will be the first in the country to test this new technology. It's called backscatter.
they came up with this backscatter X-ray technology.
Been around
they're still using this stuff at the airports
for a while, but never
in the United States
used because people were worried about privacy issues.
So they adjust the frequency just so that it goes through your clothing.
The TSA says it's found a way to refine the machine's images so that private areas can be blurred.
All right, guys, don't comment on it. No one is going to blur anything. Because if you're carrying explosives or whatever, where do you suppose you're going to be hiding that? So they're not going to blur anything. If you're a guy, if you're sensitive about your size, just put a cucumber in.
But bombs and other threats would still be detected. Passengers can opt out by choosing the traditional pat-down.
All right, the only thing you need to know, I don't care about the details. So this is going to be a higher frequency region. Higher the frequency is, the lower the wavelength is, the more dangerous it becomes. It'll go through your body. It'll go through your skin. It's going to go through your body. All right, so now we are dealing with something called ionizing radiation. Ultraviolet and above is considered ionizing radiation, which means that when this radiation comes in contact with the electrons of atoms, they can knock electrons out of your atoms. Okay, so potentially it can cause genetic damage. It can cause, depending upon the radiation level, for example, next level, these are the gamma rays, that can also cause radiation poisoning. So we got the gamma rays. This is the highest frequency range. Higher the frequency is, smaller the wavelengths are. All right, so the wavelengths are going to be the sizes of the atomic nuclei. So which means that they're highly ionizing. They can destroy your DNA. They can cause radiation poisoning, cancer, and all sorts of stuff. All right, so the gamma rays. The gamma rays are usually generated by the excited nucleons. All right, so the excited electrons generate light, excited protons within the nucleus. If you can get them to jiggle around, they end up generating these gamma rays. All right, so this is the highest frequency range that we are dealing with.
Back at the workshop, it's time to test microwave myth number 2, that microwaving metal makes the oven explode.
You know, I once had a roommate where I accidentally put a spoon in my coffee cup in the microwave, and he refused to use it ever again, made me buy him a new one. Wow. It's just those kind of misconceptions I want to clear up here on Mythbusters.
Yeah. It's time for the first metallic test subject. No, nothing happening there.
Spoon's been in there for 2 minutes, I don't see nothing. Turn it on.
So the question is, microwaving a metal, will it cause the microwave oven to explode? Now, this is a good question because I had a physics book 20 years ago, or 25 years ago. It had a huge paragraph on it. And the author was convinced that it would cause an explosion. All right, so, and here's what Mythbusters end up finding.
So, I mean, I'm guessing if... The spoon was really hot. That spoon was really hot, but it didn't do anything. I mean, it didn't arc, it didn't, like, buzz or, you know, all that stuff.
Something else from the silverware drawer, perhaps?
Fork in the microwave.
Maybe the sharp prongs will cause sparks to fly.
Oh, yeah, that's true. Not a thing.
Adam and JD have heard that tinfoil scrunched into a ball can have an effect.
Well, that's cool. Really something out of Star Trek. It's beautiful, actually.
Now, that's interesting. The microwaves are causing an electric charge to build up in the metal. Scrunching the foil allows the charge to jump the gaps. Jamie tries again, this time folding the foil into an accordion shape.
Whoa! The Hyman with the precognitive technique. Look at that!
That's the best.
Dude, you are the man. It just goes.
Spectacular, yes. But explosive? No. A warning, though. Microwaving metal might result in magnetron meltdown.
So metal in a microwave, is it true or is it false?
Well, that's false with provisions. Only in the case of an object that is made out of metal that is contacting the sides, you can create some arcing there that would feed back into the magnetron and reduce its lifespan.
Back at the
It's false.
workshop.
Coffee cup in the
There's no reason for it to explode.
microwave, and he refused to use it.
The only thing that happens is you just keep jiggling the electrons inside the conductor this way and that way. Eventually, things will heat up.
Is it ever again? Made me buy him a new one.
And obviously, if you have two metal pieces near each other, it may cause sparks flying between those two.
Wow.
The interesting thing is, the thing that amuses me most is this thing. All right, so he's got an aluminum foil on his head, and there's a reason for it. They kind of know that there will be sparks, so he doesn't want to get hit by the sparks. If he does, obviously he wants to protect his brain. Okay, so he's just trying to come up with some kind of a Faraday cage, so to speak. But for this to work, what needs to happen? This needs to be grounded. So he's kind of living with the right idea. I thought he was being goofy, but I think he really thinks that that's the best way to protect himself. All right, so let's talk about the cell phones. Are they dangerous?
Come on.
You have reached the Department of Planetary Science. You the extension of the person you're calling. Ow, Jesus! That number down.
Yes, smoking can kill, so can cell phones, but it's the same, right? It's just a distraction. Most people die with cell phones because they're texting and driving at the same time. So the question is, radiation-wise, are they dangerous? Well, it depends. It depends on the portion of the electromagnetic wave spectrum that the cell phones use. All right, I got news for you guys. They don't need radio wave, TV and radio wave frequencies are taken up for commercial as well as military usage. There's nothing available. So the cell phone companies cannot use that. And if you're Googling this information, the sort of stuff that you will get is, oh, it's a really high frequency range of radio waves. There's no such thing. All right, so once you hit that range of trillion cycles per second, that's it. That's where the radio wave frequency range ends, and then the next range starts, which is the microwave region. All right, so the microwave, the cell phones operate within the microwave region. And the reason why you would not know about it is fairly obvious right now, right? Because the cell phone companies would not want you to know that you're using microwaves for communication purposes. And all of a sudden it becomes alarming because we also use microwaves for cooking purposes. I got news for you guys. Every time you use your cell phone, you're using microwaves. Wi-Fi is once again microwaves. Your landlines, all right, microwaves, once again. If your phone, the receiver, if it's not connected to a landline directly, if you can just walk around in the house without a wire attached to it, you're still using microwaves, which means that we're bathing in microwaves as we speak. Even during this presentation is possible because of, once again, microwaves. We're using Wi-Fi. So the question is, are they dangerous if we're using microwaves?
Good evening, and welcome to 20.
So that became the investigation roughly about 20 years ago, and then debate still goes on today. People are still debating it. Obviously. So let's talk about that.
20 Friday, it is a frightening possibility that refuses to go away. Could
let's check to see what physics has to say about it.
The cell phones you and your children use be a danger to your health. A new British study just out says that while there is not enough evidence to prove harm, children should restrict their use of cell phones. And we'll tell you more about this later. But this isn't the first troubling development. Last fall, we brought you a report from our chief investigative correspondent, Brian Ross, looking into a possible link between cell phones and your brain. What he discovered could change the way you and your family use your cell phone.
From Los Angeles to London, few people spend more time on the phone than the flamboyant British billionaire Richard Branson.
Hello, it's Richard Branson.
The man who created the Virgin Records and Virgin Air business empires. The man who 4 times tried to go around the world in a hot air balloon. Richard Branson has become rich and famous by taking lots of risks. But one risk he says he won't take is with his cell phone.
Do not put your phone up to your ear because it could fry your brain.
Branson won't put a cell phone anywhere near his head, using a small headset contraption instead.
There's the phone. There's the earpiece, and just keep the phone away from the body, and put the earpiece in either ear. And you've got a little microphone here, and you can talk.
It's something he's done ever since a close friend, who was a heavy user of cell phones, died from brain cancer.
Right.
The $200 billion a year cell phone industry maintains the scientific evidence doesn't support any such fears. But it turns out Richard Branson is not alone in his belief that cellular phones can no longer be presumed to be safe.
I'm on this thing every day.
In fact, even the man who 6 years ago was brought in by the industry to quell such fears, Dr. George Carlo, is now prepared to publicly say that has been the case all along.
You cannot guarantee that cell phones are safe. That's absolutely true, but that has always been true.
When cell phones first came out, it was widely assumed there couldn't be a risk because the power or radiation they produce was so low. But now that assumption is very much being called into question by several new scientific studies, which, while still preliminary, are regarded by some scientists as quite troubling. The cell phone transmits a microwave signal from the antenna to a base station or tower, often miles away. The farther away from the tower, or if the phone is inside a building or a car, the more power this phone is told by the tower to send out to make or keep the connection. Depending on how close the cell phone antenna is, as much as 60% of the microwave radiation is absorbed by and actually penetrates the area around the head, some reaching 1 inch to 1.5 inches into the brain.
And if I hold it to my head like this, there is no way that I can avoid getting a sizable amount of that energy in my head and my hand.
Dr. Ross Eady at the University of California, Riverside is widely regarded as one of, if not the most respected scientist in the field, a man who has worked for industry and government for decades studying microwave radiation.
This is the first generation that has put relatively high-powered transmitters against the head, day after day after day.
Choosing his words carefully for this interview with 2020, Dr. Eady says the body of research, while still far from conclusive, raises the possibility of some very serious harm from extensive exposure to cell phones.
The picture that's emerging is that over the lifetime of the individual, you may see changes that could be considered health effects or potential health risks, including leukemia and brain tumors.
Those are scary words. Brain tumors, leukemia.
I understand, and I think responsibly, one has to bring those into the forefront.
Which may come as quite a surprise to the more than 80 million Americans and some 300 million more around the world who use cell phones.
Just like checking for messages.
And who heard similar concerns 6 years ago, dismissed as unfounded scares.
Hi, happy birthday.
I believe that the cellular phone is safe.
Thomas Wheeler is the president of the cell phone industry's trade group in Washington, D.C.
Our industry has gone out and aggressively asked the question, can we find a problem? And the answer that has come back is that there is nothing that has come up in the research that suggests that there is a linkage between the use of a wireless phone and health effects.
Nonsense. In a word, simple, nonsense.
Dr. Louis Lesson is the editor of Microwave News, a widely read and influential trade newsletter, which tracks the cell phone business and frequently criticizes what Lesson says is the industry's attempt to ignore or spin troublesome scientific findings.
This is about PR, not about science. There's research from Australia, there's research from England, Denmark, Sweden, Norway, Germany, all pointing in a direction Mr. Wheeler doesn't want to look. Essentially, we have reports of headaches, of cancer, of changes in blood pressure, changes in sleeping patterns.
Among the most recent work, that of this Swedish doctor, Leonard Hardell, who studied phone habits of brain tumor patients. While Dr. Hardell found no increased risk of cancer overall, he did find that those who used the phone on the left side had a predominance of tumors on the left side. Those who used the phone on the right side had a predominance of tumors on the right.
This is an important indication, and as a manufacturer, I would be actually worried.
His pilot study was nowhere near big enough to be scientifically conclusive, but enough for Dr. Hardell to recommend that cell phone users take steps to minimize their exposure and be especially cautious about children using cell phones.
There is no smoking gun. We don't know that they're unsafe, but there is tons of information from all over the world showing a problem.
But there's no sign the cell phone industry sees it that way.
A whole new way to use your wireless phone.
If anything, the industry's current ad campaigns encourage consumers, even children,
Hey, Dad, I need a ride home.
to use cell phones much more than they do now.
Doc, all you want, your family. I'm a big bucket guy.
Use it how much, you say?
I mean, I buy the big bucket of minutes, which is, 1,600 minutes, and then go beyond that.
The industry's Thomas Wheeler says there's no reason to cut back cell phone use, and that the focus in studies like Dr. Hardell's should be on the positive findings.
Dr. Hardell, in his study, says that he could not find a link between the use of a wireless phone epidemiologically and brain cancer. What he did find was an interesting handedness issue.
Interesting.
And
he says, based on his findings, he would recommend people use cell phones as little as possible. My question to you is, would you agree with that advice?
I think that there's a preponderance of evidence that there is not a linkage between the use of wireless phones and health effects.
This is hardly the first time health concerns have been raised about cellular phones.
Can you recognize this as being the phone you used?
Yes, I do.
Is this the phone?
Yes.
6 weeks after this videotaped deposition in 1993, Susie Raynard of Tampa, Florida, died of brain cancer. Her husband, David, claiming his wife's cancer was caused by her cell phone.
The tumor was exactly in the pattern of the antenna.
David Raynard went on to almost single-handedly create a national scare when he filed a lawsuit and went public with his allegations.
Well, we're suing the carrier, we're suing the manufacturer.
There was great alarm on Wall Street, and even though Raynard's lawsuit was later thrown out by a judge for a lack of reliable scientific evidence, it left the cell phone industry with a huge public relations problem.
Here today.
And led to the announcement of a $25 million industry research program to be run by Dr. George Carlo, a public health consultant who was labeled then by some as a kind of scientific shill for the cell phone industry.
Do you think they thought they had bought you?
I hope that they didn't, but I think that they probably did.
And now, after 6 years of running the industry's research program, Dr. Carlo has come to a surprising conclusion, forcing him, he says, to break ranks with the industry, to add his voice to those increasingly concerned about the safety of cell phones.
We've moved into an area where we now have some direct evidence of possible harm from cellular phones.
In a revealing interview with 2020, Dr. Carlo said he felt he had no choice but to blow the whistle on what he says has been going on behind the scenes.
The industry had come out right after that program and said there are thousands of studies that prove that wireless phones are safe. And the fact was that there were no studies that were directly relevant.
Meaning no studies directly relevant to cell phone exposure. But there are now, including studies Carlo oversaw and that the industry approved and paid for.
And this simulates exactly the type of...
Clearly suggesting two potential problems, according to Carlo. Genetic damage, based on laboratory tests involving human blood. And an increased risk of a rare type of brain tumor, based on a study of brain tumor patients, although no overall increase in cancer was found.
The type of tumor is consistent with the idea that it could be affected by the radiation coming from the antenna.
But if these phones were so bad, wouldn't we be seeing thousands, tens of thousands of people with brain tumors right now?
Not necessarily. The technology has not been around that long. Cancer is a disease that has a long latency period. It usually takes 10 to 15 years for tumors to develop.
The industry says Carlo, who started his own website with online sales of consumer manuals about cell phones, is just trying to profit from his statements. And some of Dr. Carlo's scientific colleagues, including the author on the brain tumor study, disagree with Carlo's interpretation of the findings. One of them is Dr. Martin Meltz, a scientist at the University of Texas and a paid industry consultant whom the industry said we should talk to.
I believe, from my perspective, that the weight of knowledge indicates safety of cell phone use.
But Carlo says the new studies, while not proving cell phones are dangerous, do contradict such assurances that cell phones are safe.
And that's something the industry knows? You showed them these same slides?
That's correct.
The cell phone industry also sought to downplay Dr. Carlo's stunning defection with this formal statement, saying, quote, the prevailing scientific consensus is that there is no evidence of risk from the use of wireless phones. No evidence of risk.
Is that true?
That's wrong.
That's wrong.
That's wrong.
Have you seen this?
It's actually quite shocking, knowing what has been conveyed to them.
Aren't you concerned when you hear those possible health effects? Brain tumors, genetic damage.
I have to look at what the responsible scientists say.
They're alarmed by this.
And they say that there is not a public health effect.
Who says that?
And they say...
Who actually says that?
This is what the FDA has said.
Not exactly. When we checked the website of the FDA, the Food and Drug Administration, we found a much more qualified position on cell phones. The FDA says while the available science does not demonstrate harm from cell phones, nor does it lead to the conclusion that they are absolutely safe.
And I have to say to people, look, I don't know. There are no answers to what you want to know yet.
So no one can reasonably say these phones are proven safe?
Not at all. Not at all.
The FDA now advises anyone with concerns to cut back on cell phone use or take other steps to avoid exposure.
It could be like the early days of cigarette smoking. You know, we just don't know at this stage. And since there's quite a big question mark over it, I might as well play safe.
Does it make a difference what kind of cell phone you use? When we come back, our test of some of the most popular models, and you won't want to miss the startling results.
All right, so what does physics have to do about this? Okay, there's a couple of things. Let's bust the myths first.
And you've got the little microphone here, and you can talk.
It's something he's done ever since a close friend, who was a heavy user of cell phones, died from brain cancer.
I feel like that's lithium, right.
The $200 billion a year cell...
It's not going to cook your brain. That's nonsense. If it did, you would have known about it. All right, so the question is, adverse health effects. Are there any? Could it cause cancer, for example? So that's what they wanted to investigate.
Inside a building or a car, the more power...
All right, so a bunch of companies end up spending a lot of money and time researching.
This phone is his current ad campaigns.
So obviously you're using microwaves, right? So what does it mean? They're relatively safe, just like radio waves. They're safe. It's not like a big deal. Except the problem happens when you put the source right next to your head. Okay, so what's the problem with that? Now it's going to penetrate through the skin. And you're thinking, wait a minute, these are relatively high wavelengths. Guys, proximity matters. All right? Infrared, for example, is higher than microwaves, right? It's safe. Infrared is safe. It's perfectly safe as long as you keep a safe distance to the source. Put your hand on top of fire, in fire, then what happens? It's going to cause all sorts of chemical reactions. You're going to get yourself burned. But if you're at a safe distance, you're fine. All right? It's going to give the warmth that you're looking for. Now you put the radiation source right next to your head. What do you think is going to happen? It's going to penetrate right through the skin. And you know it penetrates because we use microwaves for cooking purposes. So what's going to happen is basically it's going to cause all sorts of vibrations. The vibrations will happen because you've got water molecules, 80% of the cellular structure. I say 8%. I don't know what the percentage is, 70 or 80. All of a sudden you get these water molecules to spin. So the question is, are they hitting the natural frequency of the water molecules? If they're spinning, what's going to happen? They're not spinning so hard that it's causing heating, but they're still spinning, which means that they're vibrations all over the place.
Encourage consumers, even on what he says was found.
The type of tumor it is...
Okay, so here's what they found out. The research results came out
exactly
probably about 10 years ago, 15 years ago.
Clearly suggesting two potential problems, according to Carlo.
Okay, so whatever they found in animal studies is exactly what they found when they were following people in Europe 15 years ago. Genetic damage, yeah, they did find genetic damage.
Based on laboratory tests involved.
They found it in animal studies here in the United States, and they found it in people.
Human blood, and an increased risk of a rare type of brain tumor.
Brain tumors, Once again, they found brain
Based on
tumor.
a study of brain tumor patients,
All right, so that's the bad news. The good news is they're usually not cancerous.
although no overall increase in cancer was found.
So there was, and then I still remember the news break when the news came out, and I was watching CNN at the time, and all of a sudden the CNN just said, "Hey, there's no link between cancer and cell phone usage." That was 15 years ago. And then, like watching the news, so ABC, CBS, NBC, they all said the same thing. It was just a simple, straightforward messaging. All right, but
The type of
because I was following it just out of curiosity. The reason why I was following it is because of the lectures. Usually, this is an interesting enough stuff most people want to know, and so I was interested in following it. The cell phone radiation, which is microwave radiation, that region is not ionizing radiation, so it's considered safe in essence. All right, so if you have the radiation next to your head, mistakenly I thought that it would not cause heating or whatever, and I'm noticing right now because I'm looking at the numbers. I'm just looking at the numbers that I'm going to share with you in terms of the frequency range. These people are hitting the brain at the resonant frequency of water. I cannot believe that the cell phone range, I figured that they would skip that region. Evidently, they're not skipping it. That's really, really insane that they're actually using the same exact microwave frequency range that we're using for cooking. All right. I'm flabbergasted. I did never checked these numbers before. I'm just looking at the numbers right now. And I'm thinking, what? I'm thinking, that's crazy. Now I can see usually the brain heats up, believe it or not, guys, because I was looking at some of the studies of the brain. When you're using a cell phone, your brain is going to heat up on that section, which means that you got water molecules at that point, they're spinning and they're causing the surrounding molecules in vibrational motion. That is nuts that they allow that to happen.
Is consistent.
So the question is, obviously it's not causing a standing wave pattern, so it's not going to cook the brain. Obviously the brain heats up though. Is that a normal thing? So the question was, could it cause genetic damage? Could it cause cancer? Could it cause tumors? All right, so that's what they were looking at, and then they didn't find any link between cancer and cell phone usage. Genetic damage, yeah. What else? Brain tumors, non-cancerous, yes. So those are the stuff that they found. All right, so the case study, let me just go over the way I was imagining it in my head, and then let me point out the stuff that I got wrong. Okay, I got the numbers a little bit wrong because at the time I was making up these lectures, this information was not readily available. Of course, we got 5G today, so they're going pretty high up in the microwave radiation spectrum in reality. Right? They're almost getting all the way up to heat, whatever that means. We'll take a look at it. So the frequency range is going to be 100 million to a trillion cycles per second. Ooh, 100 million to a trillion cycles per second. So that's going to be the microwave frequency range that we're looking at. All right, and cell phone region that we have to look at is, okay, let me just get my numbers right. Okay, let me just go with the numbers in my head first, and then let's go make an adjustment. Because in my head, I used to think that for whatever reason, the water molecules had a resonant frequency close to a trillion cycles per second. So I wasn't really, in my head, that kind of made sense. Because if it's around a trillion cycles per second, you start spinning these water molecules, it's going to cause all these vibrations. The vibrations will be over a trillion cycles per second. As a result, you end up getting heating. Evidently, that sort of thinking was not exactly correct. So what's happening is the water molecules are, they have a resonant frequency. The resonant frequency of the water molecules are more like 2.4. It's going to be 2.5 gigahertz. So it's going to be 2.5 billion hertz. So if you go up to a trillion, if this is 1 billion, 2, 3, 4, 5. So evidently the water molecules resonant frequency right here. All right. And it's well within the cell phone range. So if you're hitting the water molecules at that frequency, what's happening is they're spinning. For whatever reason, I thought that the spin of the water molecules would be taking place at a much higher rate. And I got news for you guys. With 5G, we go up to 5 billion. That's half this number, including the microwave oven range is also included within that region. Okay. All right. So what we're looking at under the circumstances is they can spin the water molecules. If the water molecules are spinning, it's causing heating. It's not forming standing wave patterns, so it's not going to cook your brain, but your brain still heats up. So the question is it still safe? The answer to that question is, yeah, it can cause genetic damage. How? I don't know if the heating is causing genetic damage. I'm not convinced that it does as yet. Okay, they see that kind of correlation. They see with genetic damage, obviously they see non-cancerous brain tumors. So that was the extent of it. So the question is, would you consider that region safe if that's the case? Let me just take you through the conclusion, the research conclusion. Number one, the cell phones will not cause cancer. They may cause brain tumors, non-cancerous. What else? Genetic damage. I don't know what the extent of the damage is, but this is what they found out. And despite the fact that it's not really publicized, there's more information that came out from one of the people working on research. This is, I don't know, 15 years ago, and this person was taking my physics class over at Harvard. and she was really struggling. She was a biology major. I think she was working on her PhD in microbiology, and her advisor recommended that she should take calc-based physics 2, and she was really struggling. She wasn't doing too well, and she was out of her own. So that day when the announcement was made, I happened to be lecturing on this one. I said, so the findings indicate that it can cause brain tumors and genetic damage, and yet there's no cancer risk. There's no cancer risk. And then she pointed out something which was weird. Remember the woman that had brain cancer, and then the shape of the tumor is the shape of the antenna. Evidently, her PhD was on this topic, and she was doing research. And what they found out is, despite the fact that the cell phone radiation does not cause cancer, if you're genetically predisposed to having cancer, it could trigger it, evidently. Right? That's the finding that they had, and she said that's the reason why if you have the predisposition for having cancer, it can trigger it. And she said that's the reason why the woman's tumor was the shape of the antenna. And so I said, well, if you give me access to your research, I'll give you research credit so you can get a passing grade on this course. So things worked out. But for whatever the reason, that research never saw the day of light of day, in essence. I said it wrong. Anyway, I don't know what happened to it. So there was the indication at the time that it may trigger cancer if you have any sort of genetic disposition. Okay. Now let's go and look at it from a physics perspective. So this is what the research indicates. Okay, from a physics perspective, what causes cancer is, all right, so from a physics perspective, what causes cancer is ionizing radiation. All right, so which means the radiation needs to have enough energy to knock electrons out of atoms and the molecules, making up the cellular structure. So it can cause genetic damage that could could result in cancer. All right, because the radiation is not ionizing radiation, it is thought to be safe, despite the fact that the researchers tend to be extremely cautious. All right, so if you're one of those people who are cautious, the recommendation is just keep the radiation source away from your head.
Maybe this isn't the best time to say it, but I think you're really beautiful.
Well, I've always been attracted to you too, Paul.
Wait, hold on one second. Excuse me?
Want to get away? Now you can with Southwest Airlines Internet Specials. Just $39 to $99 when you purchase by January 9th.
Bluetooth devices, some people usually wear these on their ears thinking that this is safe. I absolutely hate them. Okay, so they're even higher frequency range than the cell phones are usually. So they're not safe. If cell phones are, if that radiation range is for whatever reason, if it's dangerous, obviously you got water molecules spinning in your head. That may not be a good thing, in your brain especially. And another thing that I hate them is awkwardness that it creates, because sometimes I have no idea who the person is talking to. Right? I mean, the last time something like that happened, I was in a bathroom at the urinal at a movie theater. The guy parks right next to me and he goes, "Hey, honey, how you doing?" And then I just jumped. I turned to his way and then said, "Excuse me," and only to realize that the guy is talking to someone else. I became pee shy. All right, so that was weird. All right, so
to you too, Paul.
Wait, hold on.
All right, so most people usually don't talk on the cell phones. A lot of texting that goes on. The problem with cell phones is if you're a guy, you're usually keeping it in your pockets. You're keeping it right next to your balls. That may not be a good thing. Again, according to studies, the sperm rate goes down by 10-20%. Okay, so does this mean that if you got your cell phone in your pocket, you don't need to use a condom? I wasn't thinking in terms of birth control, guys. I'm talking about genetic damage. And if it is true that it can trigger cancer, obviously you don't want to have testicular cancer. All right, so the best thing to do is if you're keeping your cell phone in your pocket, just turn it on. Okay, when it is on, it's always communicating with the cell tower, obviously, which means that the radiation is always going through your body, and you don't want to have that. Or do what women do: you just get yourself a manly person and just put it inside. All right, that's the best, safest thing that you can do. I usually don't keep those kind of things on my body, and when I do, it's usually turned off. And don't have your cell phone in your bed and next to your head while you're asleep. That sort of stuff is dangerous.
What's like, babe? Excuse me?
So from that,
want to get away?
If you're keeping a safe enough distance, I got news for you. This radiation is completely harmless. So the proximity matters. Cell phone, not the cell phones. The microwave radiation is everywhere. It's everywhere. Right? We are bathing in it. It's everywhere.
Now you can.
All right, so I wouldn't worry about it too much. Okay, so one last thing that I wanted to share with you, and then I'm gonna call it quits for today. All right, so the stuff that I was talking about is here, guys. 5G goes up to 5G, so it goes up to 5 billion cycles per second. So you notice that the microwave region can go up to 1 trillion cycles per second. All right, so this is 5G radiation range that you're looking at. Notice that the microwave wavelength is going to be 2.5, so it's going to be here. And what you got your Wi-Fi router. The new ones are going up to 5G, so that kind of makes sense. All right, this is considered non-ionizing radiation. Does no damage to DNA. Okay, so it's a bit of a mystery. I would be cautious. That's what I'm getting at. just because it's non-ionizing, remember you have the source right next to your body, that becomes a problem. It becomes a problem for me because regarding non-ionizing radiation, heat is also non-ionizing radiation, but I would not put my hand on top of fire. All right, so I would keep a safe enough distance, because if you put it right next to your skin, it's gonna burn you. Even light, which is harmless, you can put it right next to your skin, it's gonna penetrate through your skin. You can see some of the veins, some of the capillaries when you put it next to your body. All right, so the proximity of the radiation source does matter. So just remember that in terms of where you keep your cell phone. And then you want to minimize the radiation, your exposure to radiation as much as possible. Okay, so that's going to be my recommendation.